Alright class, so today we are going to start a new chapter which is related to finding out the strains through experimental means. Now the reason this chapter is necessary because um, anything you do on computer, anything you do when it comes to mathematics, it has to be verified through experimental results. Now, if something cannot be verified through experimental results, uh, that thing, it is extremely questionable because if something from the mathematical world is not translating into the natural world, it means that we have missed some of the variables which we should have included. And also, if let us assume let us assume that you have worked out a certain model of a certain system, okay, but once you implement this model in a real world, the answers you are going to get, if you are getting answers that from the real world that is not confined that is not in you can say in accordance with the mathematical model, it means that if you were to go with it, you were going to have serious consequences. You can have accidents, you can have failures that will going to lead you to the loss of life, which is why experimental work is always the last stage. Even if it is Tesla, even if it is Lockheed Martin, or any organization you can think of, they always have an experimental work on that model. Okay? So the more the mathematical model is closer to the experimental model, the more we can assume that our work, or you can say our model is close to the uh, is closer to the perfection. Okay. So when it comes to strains does not have to be measured on a macro level. I mean, you don't have to see it with your naked eyes. Even on a smaller amount of strain can produce enormous accidents in a system, which is why strains are not desirable. At sometimes it's desirable, at sometimes it's not desirable. Sometimes we do have tolerances for strain, but what we are most interested in is to calculate the strain at the minimum level. Okay, so the rationale behind it is that the number one, the complex stress analysis problem in which a complete theoretical solution may not be possible, may not be practical without degree of difficulty, time or cost. Now let us assume that you have designed a certain systems on a MATLAB or on ANSYS. Such a system requires a lot of computational power from your processor, and what could happen is that you can let us assume that you were working on a system, and that system is actually taking 3 days to complete an analysis. But what happens is that after at the end of the third day, you realize that you missed certain variables. Okay, so when you have missed certain variables, and now you are going to do, and after you have included those variables, you are not sure if these are the complete variables or you have to perhaps modify it. You have to wait for 3 days in order for the computer to actually uh, I mean to actually give you the results of the modified model. Okay, so if you analyze the modified model, it will be at least 6 days. Starting from the day one, it will be 6 days. But even then you are not sure, that maybe you are perhaps missing some complexity, or certain factors. Or let us assume that you are not missing any kind of factors and you have accounted for all of the factors. There is still certain level of complexity that cannot be imitated in a computer. Okay, there is always a limit a computer can analyze. ठीक है. For higher mathematical calculations, we do employ supercomputers for that. For example, the Chinese have developed a supercomputer that is helping them to uh, made a fifth generation stealth fighter. So because when you have a jet fighter, the amount of air that is hitting the jet and the way it will going to behave around the the model of that jet, it is extremely complex. So you either do that in the tunneling, which is the equivalent of the uh, experimental version for aeronautics engineering, or either you do that with the help of supercomputers. Now, even if you utilize the wind tunnel system for experimenting with the fighter jet models, uh, even there is a certain limit to that also. Perhaps you won't be able to find out, like for example, the model is I mean, it may not reflect the conditions at the upper atmospheric level, because there may be certain things that are different. Okay, so at that point you actually need a computer who actually can perform analysis for you, but those computers are not available for at a university level, or perhaps at your level, or at a commercial level or at a corporate level, simply because a company cannot afford such a big computer, or only the military has access to such a computer. Hence, now the best trade-off would be is to use an experimental model in that place. Because so here an experimental model will be much more affordable than a supercomputer. Okay, simply because of the cost. Because accessing to a supercomputer requires a lot of money, and you're going to have a lot of clearance. So that could also be a factor. And I don't know, perhaps maybe even a supercomputer cannot model many realistic variables and which are present in the real world. It could be, I don't know, but I'm sure anything that is created by human has certain limitations. So, uh, so theoretical solutions can only can only be verified through experimental ways. So, which is why the experimental stress analysis is employed to verify the mathematical model. Also, the structures but subjects to change of loading conditions. Now, it could be that the system is dynamic, like for example, under certain conditions of the machine behave different, or let's say it changes its motion, or the boundary condition may change. For example, after a certain application of load, its temperature may change. So in order to account that that those dynamic conditions, we tend to move towards the experimental work. It says the design changes can be scrutinized quite effectively. It means that whatever the shortcomings which we could face during the design phase, uh, after we have done with the CAD/CAM designs, the ANSYS analysis, we can finally see that in the real world, and we can verify if there are certain things which we were not able to find out through softwares, or probably other technical uh, I mean other high-end softwares. ठीक है. So the last thing is the verification of theoretical results. Now this is the most important thing. Now if you can make as many computer model as you like, but the real game is how it performs in the real world. So even after the Lockheed Martin develops all kinds of models and analysis, it has to be tested although at a very simplistic level, but it has to be tested in the real world. Every kind of model before it goes to before it goes from the stage of prototype to the to the large scale manufacturing, it has to go through the experimental model. So in the experimental model, we have to account for all kinds of strains and stresses. ठीक है. So the commonly used methods uh, are the strain gauges, the photoelastic, brittle coating, X-ray diffraction, thermoelastic analysis. Now, we normally use the electrical resistance strain gauges in most part because they are more accurate, they are more easy to carry, and they are less costly as compared to the other techniques. But depending upon the application or perhaps availability, we can use other techniques as well, but we are mostly focused towards the strain gauges in this chapter. So strain measurement techniques could be the mechanical extensometer. It could be optical in nature, where you see the responses of the wavelength of light that is reflected back at you, and you see that change length and find out if there were changes in the material. Acoustics, but it is less common. It works like the radar, that it throws away this a wavelength at a certain frequency, and it is received by the receiver, and that you analyze its this reflected wavelength, and you see if there are certain changes, and according to that changes you make certain decision. But uh, it also can be costly, and it may not be very accurate, or perhaps it may not be very handy. So the electrical based ranges could be resistance based, capacitance based, inductance based, based upon the application or the environment in which we are trying to क्या कहते हैं calculate the strain. Now the mechanical methods, for example, includes two devices, which is the extensometer, which you can see here, and the deflectometer, which you can see is trying to uh, find out the minimalistic amount of strain by deflecting the beam or the member. Sorry guys, I'm a little sick, so my voice, I'm apologize if my voice is not clear, but I hope it's clear enough. So the important point is the stress cannot be measured directly and must be reduced from strain measurements. Stress strain relations. So if the stress is force per amount of area, and if a stress cannot be measured unless it is coming out of strain. So if we know the strain, we can put back its value into the formula, and we're going to get the stress. So you can say that strain is actually a response of the stress. Okay, so stress cannot be measured directly. In most cases, strain can be measured only on the free surfaces, therefore a plane state stress will be considered. So normally that if you have a certain body, you would not want that body to have certain shear stress, because it can so let us assume that if you have, wait a second. Now so if you have a strain gauge here for measuring strain, and if you have a certain shear stress, it somehow may क्या कहते हैं it may interfere in the strain, and the result may not be that accurate, which is why we tend to choose free surfaces that does not have any kind of shear strain. In such cases, only three independent measurements are necessary to establish the complete state of stress. Okay? In fact, this state of stress by many in fact, this is of interest by any analyst, since to a large extent maximum shear uh, stre- states tends to of developing at free surfaces. So there's nothing to explain here, since and on free surfaces, principal strains are the major cause of producing strains. So that's the principal interest of for the person who is analyzing the strain. strains are generally not uniform, so they can vary. They do not have to follow a constant rate. The determination of strain is possible over some finite length, not at a point. So strain is not a point phenomena, but is rather the whole of the member actually uh, uh, goes through the process of expansion or contraction than just a certain point. The error involved in the measurement depends on the strain field and the length of the strain gauge. Okay, we will going to study the error in the future slide. All right, so now what we have considered an area. Okay, this is an arbitrary area, and this is y-axis and this is an x-axis, and we have considered point O, and there is a certain line whose length is L naught. We have considered this small section, and there is a point on the line x1 such that x1 is equals to L naught upon 2. Okay. Now, if a force is getting applied here, obviously it will going to undergo a certain amount of strain. Let us assume that it stretches to Lx, and Lx is the new length and L naught is the original length. So delta U will be Lx minus L naught. Okay. Now the strain along the x-axis will be given by this equation, and this is just a reference that this is the state of strain along all the three axes with their shear strain as well. But since we are considering in the uniaxial direction, which is the x-axis, so we're going to display the strain through this equation. Now, the thing is that we have three possibilities. The strain can either remain constant, the strain changes linearly, and the strain changes quadratically. Now, the error is that in the author mentions that in case 1 and case 2 there will be no error, and this is if you see the notes, it is demonstrated to you how the error will be 0. The error will be the along the length of this line, the strain produced will be average. Okay, but at this point the strain will be ex1. Okay, so the error is e average minus. So for case 1 and case 2, the error is 0. Okay, but for case 3, the error is not 0. So for case 1 and case 2, you can refer to notes how they actually reach this result. The simplification is quite easy. You won't be having any kind of trouble understanding it yourself, because there's nothing to explain it. It's just pure mathematics and integration. So case 1 and case 2, you can refer to the notes how it's proven that error will be 0. However, in case 3, it is also present there, but author has established that there will be some error in the quadratic change in the strain. Okay. So the quadratic change in strain will be given as exs k1x square plus k2x plus k3. Now for average, we will going to integrate from 0 to L naught. Okay. So we will going to get this value of E average as this one. Okay. And now to get the value of strain at x1 at L naught upon 2, simply put this in this equation. Okay. So you will end up with this equation. Okay. So now you have to subtract this from this. Sorry. you have to subtract this one from this one, and you will going to end up with this equation. So this is the error of which we will going to have if the strain changes quadratically. Okay. Now in this derivation we will going to find out the electrical resistance gauge. Now you know that the resistance is directly proportional to length, but it's inversely proportional to the area. And if you remove the constant, you are going to replace with the constant with rho. Now if we simply apply derivative on both sides and divided by L, you will going to get this equation. And wait a second. Sorry, so you differentiate this and divide this by R, you will going to end up with this equation. Now all you have to do is to just break it up, and by that I mean that we know that nu is equals to E of trans upon E of axial. So even simplifying it further, we will going to get this. And what we have to do right now is to find the so if you just put it there, and df upon df it will be 1, and you take it on the other side, you will going to get df upon d naught as so so we get df upon d naught as 1 minus vd upon L. And now d upon dA, we're going to find out by it is simply delta A upon A. Change in area will be the change in the diameter, sorry, pi d square. So area is pi d square, so change in area will be pi df minus pi d naught, and simply this will be cancelled and this will be considered into the whole square. Okay. So d naught to d naught will be it will be cancelled, so df upon d naught whole square and minus 1. So this is what we have here, this is the whole square, sorry, so it's minus 1. So we know that df upon df is 1 minus vdl square. You simplify it and then you will going to end up with this. So d upon dA is equals to this. Okay. Similarly, the putting of the values, the equation 1 becomes this, and if you simplify it, you will going to end up with this. So this is the gauge factor. So the gauge factor is fixed for certain materials, or and it is says that it it appears that it is calculated by using the material properties, or the so one thing more we have to realize that is the material properties is something very important when it comes to designing gauges. Normally the strain gauge that is currently being produced is made up of, wait a second, let me check. So the most precise gauge which we are able to form, and which is being commercially produced, is the electrical resistance type, and it is made up of ultra thin foil which is photo attached. Okay, and it has the length of 0.008 inches. Okay, so yes, the material matters a lot when it comes to measuring क्या कहते हैं gauges. But one thing more is that if you see here, the error is directly proportional to the length. Okay, but so what we the point is that the lesser length we use, the more harder it is for us to make a gauge. Okay, but the more precise it will be. Okay, so to make a certain gauge, more compact and shorter active length is produced, and gauge lengths are constructed with many loops. So the gauge length is mainly like this, is this in nature, much like the, let's see a few slides below. If you can see here, yes, this is the gauge in real life, and if you can see here, these are very small lines here. So the small lines are like this. Okay, so this is how the strain gauge is formed by using the क्या कहते हैं, the material in loop form. ठीक है. Now we're going to start the Wheatstone bridge. Now we will going to study the Wheatstone bridge. So the principle behind the Wheatstone bridge is that if E equals 0, the Wheatstone bridge will be in a balanced state. It means that there is no strain produced. However, if the E is not equals to 0, there is some strain that is produced in the system. So how does this work? So consider such a circuit in which we have R1, R2, R3 and R4, and we have point A, B, C and D. Okay, so the voltage across A and B will be given by this equation, which is R1 upon R2, and V, which is V is the total voltage in the circuit, and similarly VAD will be R4 upon R3 and R2. So so across AB is R1 upon R1 and R2, and when it comes to AD, it's simply R4 divided by R4 upon R3. So this is not VCD, is actually VAD. Okay. So because we want to find E, and E is actually, if you see, it is the potential difference between B and D. So the potential difference is with respect to 2 points. Okay. So the 2 points will be VAB and VAD. Okay. But we have worked out VAB and VAD. This is VAD, this is not VCD. Okay. This is a printing mistake. So if we put out these values in this equation, we will going to come out with this equation. Now if E equals 0, okay, R1, the product of R1 and R3 will be equal to R2 and R4. In this condition, the Wheatstone bridge will going to give you 0 change in resistance. It means that there is no strain in the system. However, if let us assume the new, if under certain condition, we have new resistance as R1 dash minus R1. So it will be delta R1. Okay, so R1 dash will be equal to delta R1 plus R1. Okay, R1 dash. Now if the resistance will be changed, the R1 will be replaced by R1 dash, R2 dash, R4 dash. Okay, so I have worked out R1, which is delta R1 plus delta R1 plus R1. Putting all of this in this 7.2, I will going to get this equation. Okay, in the matrix form, and this will I'm going to name this at A, and I will going to name this as B. And if I am going to simplify, and under this condition I will going to get A as this and B as this. Okay, and if I put these values in equation D, okay, I will going to get this form of equation. And if for the sake of simplification, if I consider R2 upon R1 as simply R, I can write this. So this is the final equation that if resistance is changed, ठीक है, how much potential difference will be observed between point A and point D, and with that, and after getting this value we'll be able to find out the strain. Now, we have to know what is the sensitivity of the Wheatstone bridge. So the sensitivity can be obtained by if I simply divide delta E by the epsilon. Okay, so this will be known as the sensitivity of the bridge given by SC. So here we are, delta E upon E, and if you simplify it, you will going to come with this equation. Now, if there are multiple gate circuits, okay, it that does not necessarily mean that there will be just 4 resistances. There could be many. So we can actually this is actually forming a pattern. If you see one, the odd ones are with plus and the negatives are with even. So it is following a certain क्या कहते हैं a certain fashion. ठीक है, so we can write this in a more general form. ठीक है, so the general form can be m equals n delta m rm and upon rm, and n will be delta r upon r, which is अच्छा, this is actually the gauge factor. So delta r upon r is actually gauge factor multiplied by epsilon. So this simply replaced it with NSGE, and if you simply just, I mean, just substitute this in place of this, and you will going to end up with this. This is the final equation of the wheat bit sensitivity. Alright, now what we are going to do is that we are going to find out the the sensitivity of the potentiometer. Now, what is actually the potentiometer? Actually, we know that delta R upon R is equal to Sg. Okay, now what this means is that delta R upon R is the, I guess, wait a second, it is called, it is the change in resistance. Now what happens is that when you applied a certain load, a change in resistance is observed, and the the devices which converts this change in resistance into the electrical current are the Wheatstone bridge and the potentiometer, and two circuit arrangement. So we have considered a similar two circuit arrangement, which is R2 and R1 connected by a potential difference SV, and we want to know the difference between A and B. Okay, so by this equation we have R1 upon R2 into B, and we have R2 upon R1 as, this is the resistance the resistance ratio, which is R2 upon R1. ठीक है, anyways, so now if let us assume that some strain is produced, ठीक है, some strain is produced and the E dash becomes equal, and delta E becomes equal to E dash minus E. So the new resistance, new change in potential will be E dash delta E plus E. This is delta E. Okay, so this is what we have written in here. Okay, as the potential difference changes, so our this will be replaced by R dash, which is the new R1 dash, and this will be replaced by R1 dash divided by R2 dash. So R1 dash will be so R1 dash will be equal to delta R1 plus R1. Okay, so this is the new resistance. So we simply put this equation, put in this equation. This is of this equation after change in resistance will be this. Okay. Now, what I'm going to do is that I'm going to simply uh, put this E over here. Okay, and I will going to simply put its value as E R1 upon R1 plus R2 into V. Okay, so I will eventually get this equation. So this is the simplified form. Sorry. Okay. Now, as you can see that delta E tends to depend on delta R1 upon R1 and R2 upon R2. So to accommodate for this non-linearity, this is actually becoming non-linear. So this delta E is now non-linearly dependent upon delta R1 upon R1 and delta R2 upon R2. So in order to account for that, the author introduced a new क्या कहते हैं value which is n. ठीक है. I don't remember what this symbol is actually called. I have to see it, but let's call it n for a while. Okay, and he has written this equation into much simpler form. Okay, and to accommodate for the complexity, the n is defined as this. Okay, no background information is given as to how this result was achieved, but so we'll take it as face value. Okay, so the sensitivity can be the change in potential difference divided by sigma. Okay, so we'll just put the value of delta E. Okay, this value divided by epsilon. And here what will happen is that the value of n is so less than 1 that it can be neglected. So we're going to finally arrive with this equation. Okay. Now they are saying consider a case in which R1 is replaced with RG, the resistance of the strain gauge itself, and R2 is the क्या कहते हैं blast resistor. So the blast resistor is actually a resistor that actually limits the amount of current in the circuit. So blast resistor is actually something that controls the value of current in the circuit. So Rg is equal R1, delta Rg will be equal to delta R1, Rb is equal to R2, but since blast resistance only limits the value and does not change, so delta R2 will be 0. Okay. So you put all of this in equation 7.6, it will going to turn out to be this. Also this is in equation 6.5. So let me check the equation 6.5 is. So this is equation 6.5. Okay. This is the gauge factor. Okay. So if you see here SC equals delta R1 upon R1. So this will be delta R1 will be Rg and Rg will be R1 will be Rg and delta R2 upon R2 will be 0. Sorry, delta R2 will be 0, so this will also be 0, and we will stay in its place. Okay. And if you apply delta R upon R as G E, this E will be cancelled with this. Okay, and you will going to come with this final form. Okay, this is the value of gauge sensitivity. Okay, now we will going to produce further modification. This voltage can be broken down. So Vg will be equals to I Rg plus R2. Okay, so if I take Rg common, it will be 1 plus R2 upon Rg. So Rg will be 1 plus R. ठीक है. So this explains how will so I will going to replace it with uh, so Ig Rg 1 plus R as shown you here. Now Ig is equal to if you know that Pg is equals to Ig square R, P is equals to I square R. This is the formula. So Ig is equals to Pg upon Rg, and it will be the under root. Okay. So so we have this without the under root Rg, and so this can be written as Rg can be written as Rg into Rg. Okay. So this will be cancelled with this. Okay. So I'll be left with this equation. So putting this value, I will going to achieve this as the final equation for the sensitivity of the potentiometer. Thank you. Okay, now let's move towards uh, the 4 cases of the Wheatstone bridge. Okay. So in this first case, what we have done is that we have, in place of R1, we have replaced with the gauge resistance. Okay, and now we will going to find out what will going to happen to the sensitivity. Okay, so we know the sensitivity equation is this. Okay, wait a second. Yeah, this is the sensitivity equation. Okay, so I can find out this value of V. So V is equals to Ig R1 plus R2. So R1 equals to Rg, because this is now a gauge resistance. So I take Rg common, and it will be 1 plus R2 upon Rg. So R2 will be equal to R2 upon Rg. Okay, so it will be equal to 1 plus R, and by same simplification I will going to arrive with this equation, and I simply will going to put it in here in this value of V, and I will going to get this. So you can see the sensitivity of the potentiometer when one of its resistance is replaced with resistance of the same gauge. It depends on 2 factors, which first is the circuit efficiency, which is this factor, the circuit efficiency, and it also depends on the gauge selection. Okay, what type of gauge are you selecting? Okay, so the gauge selection will going to define Rg, okay, and Pg. Pg is the power of the gauge. Okay, and Sg is already given in the So, but it also depends upon the gauge. It's the gauge factor. Okay. So Sg is, I guess, if you remember, we have delta R upon R. We have Sg. Okay, so it's very much dependent upon the material of the gauge factor. Okay. So now let's move to the next. Now, in this arrangement, in case 2, we have this was R1, this was R2, this was R4, and this was R3. Okay. So we have, in place of R2, we have replaced it with a dummy resistance whose value is equal to R1, and R1 is replaced by gauge resistance. So both R1 and R2 will be equal to Rg. Okay. And we know that V is equals to Ig into Rg 1 plus R. Okay, if you remember. So let us assume that wait a second. Yes, so R1 plus R2. So sorry. Okay. So V is equals to Ig R1 plus R2. So both R1 and R2 are equal to Rg. So it will be equal to 2 Ig Rg. Okay, so 2 Ig Rg, and substituting n equals 1 and R equals 1, because R2 upon R1, because R2 and R1 are same, so R will be 1. ठीक है. So substituting n equals 1, r equals 1, and the value of v in equation 7.6, which is 7.16, I'm going to get this as wait a second. Okay, so this is the sensitivity of the gauge. Wheatstone bridge, if one is replaced by the active strain gauge and other is replaced by the dummy resistance. Okay. Now let's come to the third case. So the third case, the dummy, this will be R1, this will be R2, this will be R4, and this will be R3. So we have, in place of R4 we have dummy, and R2 and R3 can be of any value, but R1 is equals to RG. Okay. So if R is not equal to R2, तो R बराबर होगा R2 अपॉन R1 के. ठीक है. तो सिमिलर केस जो हम लोगों ने पहले देखा था, जो कि केस 1 में था, वहाँ पे भी ये चीज़ थी, R1 बराबर नहीं था R2 के, तो IG RG 1 प्लस R. सिमिलरली हम यहाँ पे भी वही करेंगे, 1 प्लस R स्क्वायर रूट ऑफ PG RG n इक्वल्स 1. तो आप वही उसमें आप 7.16 में डालेंगे तो आपके पास यही इक्वेशन जो ना दोबारा आ जाएगी. तो इससे पता चल रहा है कि अगर if you replace dummy with resistance 4, it will going to convert into this case. ठीक है. देखिए लिखा हुआ, the circuit sensitivity for this bridge arrangement is identical to that which can be achieved with the bridge circuit as shown in case 1. Thus the temperature compensation can be obtained without any loss in circuit sensitivity only if the dummy gauge in place of R4. So the circuit temperature compensation means that temperature induced resistance. Okay. Here the temperature compensation is the temperature induced resistance. So it's saying that to compensate for that temperature, क्या कहते हैं, to compensate for the temperature factor without losing the circuit sensitivity, we can simply replace R4 with the dummy resistance. ठीक है. Now this is the fun part, and all resistances are you might be thinking that what if we replace R3 with the dummy. Okay, but I think that it will not going to have significant effect, which is why we do not have such a case. Okay, so which is why the author of the book did not place dummy in place of R3. Okay, so now we have a case 4 in which we have all the active gauges in place of all resistances. So we have again similar, R1 is equal to R2. Okay, when R1 is equal to R2, we have the same condition. Okay, so now let's read the conclusion. Since the resistance is same for all 4 gauges R1, the circuit sensitivity for the bridge is obtained by substituting equation 4 in equation 16. So it is the same thing, I guess. Wait a second. So this is the equation 7.16. Okay. So n will be equals to 4. Okay. The reason behind, because there are 4 gauges we have 4 gauges here. In all the previous example we have only 1 gauge. So n was always equal to 1. Okay. But we have 4 gauges here. So V is equals to 2Ig Rg into this will be 1 upon 1 plus 1, so it will be 2, so it will be 1 upon 4, so it will be 4 and it will be Sg, so 4 cancel, so it 2Ig Rg and Sg. Okay, so 2Ig Rg will be equal to this is how the 4 cases of Wheatstone bridge will be done. Okay, so these are all the equation for sensitivities in each case. Okay. So now let us move on to the last क्या कहते हैं. So we have arrangements in which we place क्या कहते हैं gauges. So if you see here, we have this arrangement is as this is the 45-degree arrangement of strain gauges. So this is actually 45, ठीक है, and this is the 60-degree arrangement, ठीक है, this is 60, this is 60, and this is the stacked arrangement. So each is replaced over the other, and we also have the star arrangement. Those star arrangement in the gauges are at 120 degree to each other. So this is the star arrangement. Okay. So these are some of the fashions in which we क्या कहते हैं we arrange the strain gauges in order to find this is the star arrangement, in order to find the strain in an element. Okay. So our main focus in this chapter will be the rosette arrangement, and we will be studying just the 45-degree and the 60-degree rosette arrangement. So one thing more is it is also called 0, 45, 90 degree. So if you can see this, if you consider this axis as 0, this will be 45 and this will be 90. Similarly, this is also called 0, 60, 120. If you consider this as 0, this will be 60 and this will be 120. Okay. So we have, since we have three strain gauges, we have to find the principal strains, okay, that is occurring in an element. Okay. So to start, wait a second. So in order to find the strains at different rosette arrangement, we first should see the equation of principal strain. So the principal strain is E1 and E2 equals Ex. So you can consider here Ex as Exx. Okay. So just assume that Ex is actually Exx. Okay. So is Exx plus Eyy upon 2 plus 1 upon 2 Exx minus Eyy square, and the whole equation is written. Okay. So all what you have to do is you have to find out the value of Exx, Eyy, and gamma xy. Okay. If you know all these, the value of all of this, you can simply put in these equations, and when you put these equations, you will going to end up with the principal strains composed of strains of elements in rosette arrangement. Okay, let me explain what